Alrighty, there you guys are. Good morning, or I guess good afternoon now. Welcome back to MAC1140, section 009, pre-calculus. Today is our second meeting. So I'm going to begin by kind of recapping a little bit of the stuff from last time. Basically just showing somebody, in case today is your first day in the class, because we're still in that add drop period, show you where to go to get the things you missed on Tuesday. Just a little bit of a warning, a heads up. My home internet is being kind of spotty right now. I do have my phone up here with the top spot on as a backup. If I just disappear for a second, just out of nowhere, vanish, I'm sorry, and I'll be back in a matter of seconds. I just got to switch over to the hotspot. But I'm not streaming exclusively from the hotspot to try and preserve that data. Okay. So this is, as always, MAC1140. You guys are section 009. It is a pre-calculus class. And today is August 26th, 2021. Today we're going to do a few things. We're going to quick recap of day one stuff. Then we're going to talk about topology. Specifically the topology of the real line. And remember, if I want to refer to the real numbers as a singular object, I will use this Blackboard bold R. Particularly here, we're going to talk about interval notation. Then we're going to talk about inequalities. And these we're going to split into two kind of sections, linear inequalities and nonlinear inequalities. And then finally, we're going to talk about finding domain. So we're going to begin with a quick recap of day one stuff. If today is your first day in class here, you either missed lecture on Tuesday or you added the class between then and now. Here is what you need in order to not fall behind. 0 things 0. You have to get to our Canvas course. Obviously, class meetings Tuesday, Thursday. Office hours are set right now at Monday, Wednesday, Friday from 1 to 2 p.m. And to join those office hours, you just click this link. If you want to meet with me outside this, that's fine. Just send me a Canvas message and we can arrange either a different Zoom meeting or an in-person meeting if that's necessary. The final exam, I need you to put in your phone's calendar if you have not. Gotta do this. It is December 7th. At 1 p.m. and that is a 2-hour test. The other thing I absolutely need you to do, if you did not do it on Tuesday, is save a copy of the syllabus somewhere on your computer where you can find it. So just click this link, save file, and then plop it somewhere you're going to remember where it is. Like I've got for you guys here a fall 2021 folder, and then a MAC1140 folder, and then I've got the 3 syllabi for the MAC1140 classes I'm teaching. I'll go ahead and save over top this one. There were a couple typos in the syllabus as it was when we went over on Tuesday. I've fixed those typos now. At least I think I fixed most of them. If you're new to the class, you need to read this. Actually have to read it. I think there is a typo that persists here. Your homework is going to be due on Tuesdays and Thursdays at the start of class. But I think everything else is fixed. Okay. So the most important thing you need from this syllabus, if you missed class on Tuesday or not, is this thing right here, which is the class key that you use to register for our class in WebAssign. So WebAssign is where all of your homework and quizzes will take place. You need to get registered for our class in WebAssign today. Even if you don't have your access code yet, the access code is separate from the class key. The access code is like your proof of purchase. It's how you actually pay for access to the course, the WebAssign course. The class key, this thing, which I provide in the syllabus, is how you tell WebAssign which class you're in. Even if you don't have your access code, you can go to WebAssign, enter the class key, and get registered for the class. They will ask you for an access code, and when they do that, just look around on the page. Somewhere on that page, there's going to be a little link that says, if you don't have your access code yet, click here to use the temporary trial access, something like that. That'll get you in for the first 2 weeks, but you got to buy your access code and enter the access code before getting kicked out at the end of those 2 weeks. So there's no excuse for not being into WebAssign. You got to get registered for WebAssign. You got to get started because you do already have a homework that is up, right? Your very first homework set is right here, and it's due Tuesday at the start of class next week. In our last class, I threatened or said I was going to release a second homework set for you guys this week on today, Thursday. But the way things have been going, the pace, people getting registered, folks having some trouble getting into WebAssign, I'm going to hold off on that. So you're going to have just the one homework set this week, and it's going to be due next Tuesday at the start of class. But generally, you will have 2. I'll try to speak up a little bit. All right. So if you missed class on Tuesday, make sure you save a copy of the syllabus somewhere on your computer. Read the damn thing, please. Get registered for WebAssign. And then the link to the recorded class from Tuesday is up. So I record all these Zoom meetings. I post them to YouTube after the fact. So here is the actual recorded lecture from Tuesday. If you missed that, you should watch it. One other thing, I guess. So let me paste into the chat now because I know it's going to come up later. If you have any trouble registering for WebAssign, use these registration help office hours that Cengage they will guide you. Right. Here's the information. Just make sure you join the meeting on your screen, not cell phone. All right, they've asked me to tell you that. Join from your computer, not your cell phone. All right, so if you're having trouble with your access code, you've got a multi-term access code and you're not sure if it still works, or you have any sort of uncertainties about how to register for WebAssign or any trouble when you do try to register for WebAssign, just follow the link that I gave you in chat there. I would suggest that everybody copy paste this out of chat and into a document on your computer somewhere you can save it in case you run into trouble with it. All right. I think that's all the preliminary stuff. Does anybody have any questions about the sort of bookkeeping, how the class runs stuff that we talked about on Tuesday? Anybody here for the first time today need anything clarified? Okay. One last little comment or word of warning. When you sign into Zoom, please use your name as it appears on your Santa Fe ID. I take roll from the Zoom logs. That's how you get marked as attended for financial aid purposes. So I really need you guys to use the name that's on your Santa Fe ID when you sign in. Excuse me, when you sign into Zoom. If it just says like John's iPhone, I don't know who to mark as having attended. And I'm not allowed to kind of guess, right? Like if it's initials or something like that, I can't like scroll through the roster and look for someone with those initials. Just way too easy to get things wrong that way, and this is too important to risk getting it wrong. If when you sign in, make sure you use your actual name. It looks like pretty much everybody's friends. I appreciate that. All right, that is our recap of day 1 stuff. If you do have any questions about syllabus or syllabus-like things, policies, homework, grades, please come by my office hours or send me a message on Canvas or send me an email. I'd be happy to talk about that stuff with you guys. We're going to begin the actual math today by talking about the topology of the real numbers. Topology is a mathematics term that comes from the Greek word topos, which I think means shape. Traditional topos. Place or commonplace, yeah. So space, I guess, is the topos is like space. So it's the study of spaces, topology. So you think of the real numbers as a space, we think of it as a line. right? We talked about this last time. The real numbers form a complete ordered field, which is a special set of rules, meaning that it's a field. You can do all the algebra stuff that we want to do. It is ordered, meaning given any two real numbers, one is bigger or smaller than the other, as long as they're not equal. And it is complete, meaning when you arrange them in order on a line, it forms a solid line. There's no gaps, there's no holes. That line is rock solid. Unlike the integers, if you were to take the integers and put them on a line, there's a gap between 0 and 1. There's a gap between 1 and 2. The real line has no gaps. So here it is. Here's the real numbers. The important subsets that we're going to deal with are called intervals. And when we talk about the topology, we're kind of trying to describe the open sets in R. An open set is like an open interval. It's a set that doesn't contain its boundary. And then there are also closed sets, sets that do contain their boundaries. Those are kind of like closed intervals or single elements. I'm gonna draw a particular set here, and then I'm going to show you how to describe those in the terminology. So in blue on my real line, these are going to be the things that I'll include in my set. So maybe -1, and then maybe here is 0, and I'd like to include 0. And maybe I want to include everything from 0 to +1, including both of those numbers themselves. So I would shade that. Draw that. Did I draw a 2 there? Let's make this one. Okay. Or maybe I want to describe some other sort of set, like maybe I'm interested in the set from 2 to 3. And I don't want to include the 3, but I do want to include the 2. And I want to include everything in between as well. Okay, so these are some different subsets of the real line, or I can think of them all together as a single subset. And I'm going to show you how to write those things in a nice notation. The notation we use for, the most common notation we use for subsets, the most commonly discussed, subsets of R are intervals. And intervals primarily come in two different types. There are open intervals. The open interval from A to B is the set of all real numbers x satisfying a certain inequality, namely A is strictly less than X is strictly less than B. Okay, so we're going to be working with inequalities quite a bit today, and I want to start here by saying if you have trouble remembering like which one is less than, which one is greater than, the easiest way to think of this, especially since we are in Gainesville, is that the inequality is like a hungry alligator. It always eats the bigger thing, right? So if you've got like X and then this symbol and then B, this thing is eating the B. So it's saying B is larger than X. So here you could say this, you could read this two ways. You could say this B is greater than X or X is less than B. Now in English, we read left to right. So we would read this as X is less than B. Similarly here, if you're comparing A and X with an inequality, notice the inequality is eating the X. That means the inequality says the X is bigger. So this says that A is smaller than X, or X is bigger than A. And again, we read left to right. So this symbol right here is a less than symbol. These are both less thans. Such a set is denoted with parentheses. Right, so if you see parentheses A, comma, B, and you know that we're talking about an interval, then that's the open interval from A to B. In other words, it's all the numbers that are strictly larger than A and also strictly smaller than B. It's all the stuff that is strictly in between A and B, not including A or B itself. If you
Hold on, I'm sorry. What's that word right there?
denoted?
Denoted. Okay, sorry, I couldn't see it. Thank you.
Yeah, just meaning the notation for which is, or like how we write it. So I write that interval as parentheses AB. Okay, so we just said this interval does not contain the number A, it does not contain the number B. It only contains the things that are strictly in between them. If I do want to contain the endpoints, that would be a set containing its own boundary and therefore what we call a closed set. If I'm talking about an interval that happens to be a closed set, I call that a closed interval. So the definition of a closed interval is the closed interval from A to B. Here in both of these, A and B are real numbers, and A is always smaller than B. We always write the smaller number first. The closed interval from A to B is the set of all real numbers X satisfying a slightly different inequality. I want everything between A and B, but I also want A and B themselves. So this is A is less than or equal to X is less than or equal to B. And this set is denoted brackets, bracket A comma B close bracket. All right. So the blue set above, I'm trusting that everybody has seen this before. I'm just kind of trying to remind you. The blue set above, I can describe as a union of different intervals and sets. So let's start over here on the far left. The set just containing -1, that's not an interval. That's not like all the numbers from here to here. It's just a single number. So to describe that set, I would use curly braces, -1. Kind of like the curly braces we used when we were writing down the natural numbers and the integers on Tuesday. So a set containing just one thing, you put that in curly braces. A set containing just two things, you would put that in curly braces also. Like if I just wanted -1 and -2, that would be curly braces, -1, comma, -2, close curly braces. This next guy, all the numbers from 0 to 1, including both of those numbers themselves, 0 and 1, that's a closed interval. That's the closed interval from 0 to 1. So I would write that like this. The last guy over here, he's a little bit weird. He does include the 2 on the left, but he doesn't include the 3 on the right. So I would write that as left closed and right open, like this. Intervals like this are called bullet shaped, and you can kind of see why, right? Picture like a little handgun bullet. It's like square on the back and rounded on the front. We call these bullet shaped intervals, but left closed, right open. That's the idea. And then if I want to describe the whole blue set here, everything that's shaded on this number line, I would union these. Right, so the shaded blue set down here in interval notation is this. All right. I think probably everybody has worked with interval notation in at least one class in the past. I'm not going to spend a whole lot more time just focused on this, but because these intervals are defined in terms of inequalities, we can get a bit more practice with them while we move to our second object here for today. So I'm going to go ahead and start talking about inequalities now, and we'll see how to solve linear inequalities, how to solve nonlinear inequalities. Turns out these are a bit trickier than these. Any questions about the interval notation or what I mean by an open interval, what I mean by a closed interval, anything like that? Okay, one little word of warning. Let's pass tab. The open interval is the same notation as a point. So make sure you don't confuse points and open intervals, right? Like if I wanted to describe the point in the Cartesian plane whose x coordinate is 1 and whose y coordinate is 2, I would write that as parentheses 1 comma 2, close parentheses, which is the exact same notation I would use to describe the open interval from 1 to 2. So you'll see me do something a lot. Every time I write down something like this, and it is an interval, I'll put the word interval before it to make clear. And I recommend you do something like that just to keep it straight in your brain. Specifically when we talk about mins, maxes, increasing, decreasing, that's a place where we use both notations, and it is possible to get confused. Just a little warning. Okay, inequalities. You have plenty of these in your current homework to practice with. And the big idea is that we break these into two categories. Linear inequalities. And I'm going to leave a nice chunk of space there. And non-linear inequalities. The reason we want to be able to categorize these is because you solve them differently. There's an easy, fast way to solve linear inequalities. There is not a super easy, fast way to solve non-linear inequalities. So when you get started with an inequality, you first need to figure out, is it linear? Can I do the easy thing? Or is it non-linear? Do I have to do the longer thing? And some nonlinear inequalities look like you could solve them doing the easy thing, but you can't. So it's a really important way to like stop yourself from making a mistake. Before I talk about how to solve them, I need to tell you what they are. So a linear inequality, this is an inequality where variables or variable shows up only upstairs, right? Not in any denominators, and only to the power of 1. So never under a root, never downstairs in a fraction, never squared or cubed or anything like that. Again, leave some space. A nonlinear inequality is an inequality, any inequality which isn't linear. Right? So if the variable shows up to the power of 2 or 3 or 4, if the variable shows up under a radical, if the variable shows up downstairs in a fraction, anything like that, any inequality like that is a nonlinear inequality. To solve linear inequalities, treat them like an equation. Isolate the variable. The only catch, just remember, if you multiply or divide by a negative, then the inequality symbol flips over. I know I'm writing a lot of words here, so I think now is a good time to remind you, anything I put on the doc cam needs to go into your notes. This is precisely what you want to refer back to study for the tests. So even though I know there's a good chunk of writing here, I'm asking you to write along with me, right? I'll give you time to catch up writing and stuff. So linear inequalities are easy to work with. You solve them the same way you solve linear equations. You just like add 5 to both sides and divide both sides by 2, that sort of shit. You just want to try to isolate the variable by doing whatever algebra is necessary, usually adding or subtracting something from both sides and then multiplying or dividing something both sides. The only catch is that if at any step you multiply or divide by a negative number, the inequality symbol will flip over. So if I divide both sides of a linear inequality by -5, then the less than will flip over to a greater than. That's it. Nonlinear inequality is more complicated. We make a number line or sign chart. All right, the book teaches sign charts. I'm going to show you how to do this with a number line. I think it's faster, smarter, and it works for more problems than the sign chart thing. Like the number line thing I'm going to show you here, you'll use it again in Calc 1. You'll use it later in this class when we talk about polynomial and rational inequalities. So it works well. I recommend you follow the procedure I show you. What do I mean by make a number line? Well, there's this step-by-step process you have to go through. So I'm going to outline some steps for nonlinear inequalities in just a second. Oh, and I just saw the question in chat. Yeah, so let me come back to that really quickly before I give you the steps for nonlinear inequalities. The U here, the union symbol, this means I'm going to take all the stuff from this set and all the stuff from this set and throw it into one box. So the union is how you join things together. It's how you take all the things from the one set and all the things from the other set and combine them into one new set. Okay, in a Venn diagram, the union of the 3 sets is all 3 circles together. Okay, so what's this procedure for making a number line or a sign chart? Okay, your first step is to pull all terms to one side. So that will make the other side 0. That's the very first thing you need to do when solving a nonlinear inequality. The second thing you need to do is combine any like terms and have a common denominator between any fractions. And there are some problems in your homework where you'll practice having a common denominator between pretty complicated expressions that have fractions with variables and stuff like that. So you pull everything to one side, and you have a common denominator. Then, combining all like terms have common denominator. Then you factor everything. And set the factors to 0. Then you plot the solutions from step 3 on a number line. And that will split the number line up into several regions. Your last step here is to then test a point from each region. So I'll explain more of the details as we get into our first example. This will make more sense. But I do want you to get this kind of algorithm into your notes. This is how you solve a nonlinear inequality. You cannot solve nonlinear inequalities the same way you solve linear inequalities. It just doesn't work. The stuff you get doesn't make sense. The algebra steps that might seem like they're valid are not. Okay, so I'm going to hold here just for a second, give you a chance to get everything written down. Right, here we go. So our first example.
I have 2 more seconds.
Sure. All right, I am going to go ahead and write down the first example now. But I'll move slowly through it. So let's solve 1 minus 3x is less than or equal to, 7. And we want to write the solution in interval notation. Okay. So I'm going to move the page up a little bit here. I'll leave this in case we're still writing anything from that. But I'm going to go ahead and get started on this. So first we got to identify, is this linear or nonlinear? Because if it's linear, then we can solve it the easy way. If it's nonlinear, then we have to go through this procedure.
Seems linear.
It is linear, yeah, definitely, right? Here's the only place the variable shows up. It's not under a radical. It's not downstairs in any fraction. It's not raised to a weird power like 2, 3, or 5 halves. This is just 3x to the 1. So this is a linear inequality, which is good news because those are easier to solve. You'll see me use this notation on the left here a lot. This double arrow, this kind of bold double arrow, stands for the words if and only if. It means that what I'm about to write here is logically equivalent to the original, meaning the solution set for the thing I write here is the same as the solution set for the thing I write there. So since this is linear, the way I'm going to solve it is just by trying to isolate the variable, just using algebra steps to isolate x. My first step there would be to subtract 1 from both sides. So if I subtract 1 from the left, the 1 goes away and I just have negative 3x. I'm not multiplying or dividing by a negative here, so the less than or equal to stays a less than or equal to. And positive 7 minus 1 is positive 6. So there's my first step, just subtract 1 from both sides. And then my second step, if I want to isolate that x, just treating this like I would an equation, is to divide both sides by negative 3. So that will give me x is greater than or equal to 6 divided by negative 3 is negative 2. And the inequality flipped here because I divided by a negative. We call it the sense of the inequality. That's the way a mathematician would say it. The sense of the inequality changed. So that's it. Anytime you multiply or divide by a negative, the inequality flips over. And now I'm done. Really, just these 2 steps, right? Now I've got x is greater than or equal to negative 2. I've isolated the x. So the only thing I have to do is get this solution into interval notation. And I think the easiest way to do that is to sketch the solution on a number line. That's when you're first getting used to interval notation. I'll just, -2, whatever, I'll put it over here. I'm interested in all the x's which are greater than or equal to -2. So anything greater than -2, that's anything to the right of -2. That's all this stuff. And that set goes on and on and on forever in this direction. So I like to bold the arrow there. And then since it's an or equal to, -2 itself should be a part of the set, not just things that are strictly bigger than it, but the number -2 itself does solve this inequality. So I indicate that by putting a filled in dot there, or you could use the bracket like that if you prefer. So how do I put this in interval notation? Well, there is no, like, this is my A, right? In A comma B, this is my A, -2 is the lower bound for my interval. But there is no upper bound. It goes on and on and on and on forever in this way. So the way we describe that is as the interval from -2 to infinity. And the infinity symbol, which is called a lemniscate, by the way, Lemniscate, lemniscate, always gets a parentheses because infinity is not a real number. There are number systems that include infinity called like the extended real numbers or the extended complex numbers. But for us, infinity is not a number. It's more like a concept. We're just saying that this solution set goes on and on and on forever that way. So this is how you would write that set in interval notation. That's it. That's your answer. So these are easy, right? Linear inequalities, just treat them the same way you treat equations. Try to isolate the variable. The only catch is anytime you divide or multiply by a negative number, the inequality is going to flip over like it did here, going from less than or equal to greater than or equal to. Any questions on this example? Okay. We'll get something a little more challenging next. E.g., for example, let's solve the inequality x squared is greater than or equal to 4, and write the solution in interval notation. Okay. So is this linear or nonlinear?
Non-linear?
Good. Yeah, this is a nonlinear inequality. Still, I bet most of us, if we looked at this, especially the first time, would have a particular idea of what to do to solve it. What comes to mind when you see this?
Square root?
Perfectly reasonable thought. The first thing's here, linear or nonlinear. And this one is nonlinear. And if this was an equation, I would try to solve it by taking square roots, right? Remember, when you take square roots, you get a plus and a minus, though. So if I were to take square roots here, I would get x is greater than or equal to plus or minus 2. And it's not clear what that means. Does that mean x is greater than 2 and x is greater than -2? Does it mean x is greater than 2 or x is greater than -2? Does it mean something else? In fact, it turns out neither of those things are true. So a quick note. Because this thing is nonlinear, we can't do the following. We can't say x squared greater than or equal to 4 is logically equivalent to what you get by taking square roots, which would be x is greater than or equal to plus or minus 2. Because this statement Doesn't make sense. Right? Think about it on the number line. Okay, here's -2, here's +2. If I say x is greater than +2, that's this stuff. Right, including the 2 itself. If I say x is greater than both of those, I could be talking about all of this stuff. Right? These are all the numbers that satisfy x is greater than -2 or x is greater than +2. Or I could just be talking about the overlap. That would mean x is greater than -2 and x is greater than +2. But none of these, neither, is correct. Neither of those is the correct solution set, not the blue, not the purple. So this sort of logic where you just treat it like an equation, that works, but only for linear inequalities. It does not work for nonlinear inequalities. The very first thing you need to do is ask linear or nonlinear. Since this is nonlinear, we can't do this stuff. We got to do the other thing, that procedure I outlined. So what's the first step in that procedure I outlined for you on the previous page?
Pull all the terms to one side.
Very good. So I start by pulling everything over to one side. I'll pull the 4 over. So this is equivalent to saying x squared minus 4 is greater than or equal to 0. There aren't any like terms to combine here, but I can factor that. So this is equivalent to saying this factors as a difference of squares. This is x minus 2 times x plus 2 is greater than or equal to 0. So my first couple steps, pull everything to one side, combine like terms, factor, and then we want to set each factor equal to 0 on its own. So if x minus 2 equals 0, then x is equal to 2. If x plus 2 is equal to 0, then x is equal to -2. So the two numbers, +2 and -2, they are going to show up here. They are important. It's just that neither of these intervals, the purple or the blue, is the correct interval that solves this inequality. It's a bit more complicated. Now that we've pulled everything to one side and factored everything, we take those two solutions that we get from setting the factors to 0 and we plot them on the number line. Okay, here's -2. Here's +2. And what that does is it splits the number line up into regions, in this case, 3 regions. Does everybody see that? I've got a region here, I've got a region here, and I've got a region here. It is a mathematical fact that any inequality of this sort, once you get to this step, will either be true everywhere in one of these regions or true nowhere in one of these regions. In other words, if any number from this region satisfies the inequality, then every number in this region satisfies the inequality. If any number from this region satisfies the inequality, then every number from this region satisfies the inequality. And the same is true of the third region. If the inequality is true when x is equal to 5, then the inequality is true for every x bigger than 2. Just a quick silly question. How many numbers are there in this middle region? Between -2 and 2. How many numbers are there?
Infinite.
Very good. There's infinitely many numbers, right? Not just the integers. So we can't check all of them. And that's why that theorem is so nice. That's why that fact is so useful. Just by checking one number in here, I'll be able to verify that the interval is solved by every number in that interval, or the inequality is solved by no number in that interval. So our next step is to test one point from each of those 3 regions. I have to pick a point to test here. I'll test x equals -3 from that first region. I have to pick a point to test in here. 0's in there, so I'll test x equals 0 from that middle region. And I have to pick a point to test on the far right. X equals +3 is the first thing that comes to mind for me. So pick easy numbers to work with. You get to pick your test points. They have to come from the interior of that region. They can't be either of the endpoints, have to come from inside. But they can be anything. I could have tested -pi over here. It's just that -pi is not as nice to work with. I could have tested 1/6 in here if I wanted. It's just that 1/6 is not as nice to work with as 0. So take your numbers that you get from the previous step, plot them on the number line, then pick a test point from each of the regions that creates. Right? I like to draw these little dividers because they help me see the regions better. What do I mean by test -3? Well, I mean plug -3 into the original inequality and see if you get a true statement. So -3 squared is greater than or equal to 4. Is that true? Well, let's see. -3 squared is 9. So it says 9 is greater than or equal to 4. That is true, right? 9's bigger than 4. So I put a check here. Every number from -infinity up to -2 solves that inequality. So that check is between -2 and 2. I said I'm going to test x equals 0. So I plug 0 into this original inequality. I get 0 squared is greater than or equal to 4. Well, 0 squared is 0. So this says 0 is greater than or equal to 4. That's not true. 0 is not bigger than 4. So no number between -2 and 2 satisfies this inequality. And then finally, to the right of 2, I chose to test +3. So plugging that in, I get 3 squared is bigger than or equal to 4. 3 squared is 9 again. So 9 is bigger than or equal to 4. That's true. So every number in this region satisfies the inequality. So if neither of these, 2 to infinity or -2 to infinity, were my solution, what is my solution? Well, here it is. It's from -infinity to -2, unioned with +2 to +infinity. The only other thing we need to do, so we know, that our solution is an interval, or it's intervals of 1. So this first region, which was good, which was -infinity to -2. And the second region, union map, the second region, which is 2 to +infinity. The only other thing we need to do is check the endpoints. For plus and -2. So I know that the infinities always get parentheses. That's just the rule. Infinities always get parens because they're not real numbers. But what about the 2's? Do I include this guy or not? Do I include this guy or not? And just like we were testing our points back in the original inequality, I'll test these guys back in the original inequality. So when x is equal to -2, we have -2 squared is greater than or equal to 4, which says 4 is greater than or equal to 4, which is true. So I'm going to include my -2 in the solution. It means I'll put a bracket there. And when x is equal to +2, I check +2 in the inequality. You could check it in any one of these versions, but the original is the easiest to work with. I get +2 squared is greater than or equal to 4, which again says 4 is greater than or equal to 4, which is true. So I use a bracket here. And that's it. That's your solution. Okay. So solving nonlinear inequalities is much more involved than solving linear inequalities. And unfortunately, this sort of stuff doesn't work. Right? You see, the solutions that we may have gotten out of thinking like this, x is bigger than ± 2, is either the interval from -2 to infinity or the interval from +2 to infinity, neither of which are the correct solution, right? -2 to plus infinity is not the same as this. 2 to infinity is the same as this, but you'd be missing this whole piece, so it wouldn't be the correct solution. In a little bit, once we get deeper into chapter 2, I'll give you a way to think about this geometrically, like using pictures. But we have to talk about graphing functions first. Any questions on what we did here or how we did it? Okay, then I'd like to look at one more example of a nonlinear inequality. And then we will move on to talking about domains. Let's look at x squared over x plus 2 times x minus 2 is greater than 0. And again, give the answer in interval notation. You guys have a number of homework problems that look like this. In fact, all of the nonlinear inequalities I gave you, everything's already been pulled to one side. The common denominator step is always done. The factoring step is always done. So we're already past those first 3 steps. This is clearly nonlinear, right? Because I've got an x squared upstairs, and then I've got these 2 variable quantities downstairs. Either one of those things would make this nonlinear. So the only thing to do is to do our number line. I set each one of these pieces equal to 0. I set the top equal to 0. That means x squared is equal to 0, which means x is itself equal to 0. And setting the bottom equal to 0, I see that these factors have to be 0, so x plus 2 equals 0 gives me x equals -2. X minus 2 equals 0 gives me x equals +2. All right, so I've got these 3 numbers that I'm going to put on my number line. And you see, this is not something where you could even try to solve it like an equation, right? Good luck isolating x here. It's not going to happen. So instead, we do this. The spacing between these doesn't matter, only the order matters. Again, I like to draw these little vertical things to help me see the regions. Here there are 4 regions, from -infinity to -2, from -2 to 0, from 0 to 2, and from 2 to +infinity. I need to test a point from each region. So over here, I could test x equals -3. From in here, I could test, there's only one integer, -1. If there were no integers between here, I just have to use a fraction, like -1/2 or something. And from the next region, I could test x equals +1. And from the last region, I can test x equals +3. So I've put down my number line, I've picked my test points, we're ready to go. I'm going to plug -3 into this expression. We'll see what we get. -3 squared divided by -3 plus 2 times -3 minus 2. And this is all supposed to be greater than 0. Okay, as I simplify, I won't write the greater than 0 because I just don't want to take up the space. -3 squared is 9. -3 plus 2 is -1. And -3 minus 2 is -5. So this is 9 over -1 times -5 is +5. And is 9/5, this number, greater than 0? Is this a true statement or a false statement?
True.
Yeah, it's
True.
true, right? 9/5, that's almost 2. It's like a 1.8. So yeah, this is true. So this region will be a part of my solution. Now, if I plug in -1 to this guy, let's see what we get. I'll have -1 squared divided by -1 plus 2 times -1 minus 2. And we're supposed to check and see if that's greater than 0. And -1 squared is +1. -1 plus 2 is also +1. -1 minus 2 is -3. And I want to know again, is this greater than 0? Upstairs, we just have 1. Downstairs, we have 1 times -3. So altogether, that's -1/3 is greater than 0. Is that a true statement or is that false?
False.
Good, that's false. Yeah, -1/3 is negative. So it's smaller than 0. That's what negative means. Okay, let's test +1. There I'll have +1 squared over +1 plus 2 times +1 minus 2 is greater than 0. 1 squared is 1. 1 plus 2 is 3. 1 minus 2 is -1. It's greater than 0. So again, I've got -1/3 is greater than 0, which again is false. And then finally, from my last region, if I test +3 here, I'll have 3 squared over 3 plus 2 is 5. 3 minus 2 is 1. And I want to know, is all that greater than 0? And you see right away, every piece here is positive. So yeah, it is. But let's crunch it out. 3 squared is 9. So this is actually going to be 9 over 5 again. 9/5. 9/5 is greater than 0. Yeah, that's true. So the solution set here doesn't include this guy and doesn't include this guy. It does include all this stuff, and it does include all this stuff. That's and it's similar to the last one, -infinity to -2, unioned with +2 to +infinity. Now this time we're looking at a strictly greater than, right? This inequality is not greater than or equal to, it's just strictly greater than. And what that means is you don't even need to bother checking the endpoints, right? These endpoints will either make the original apparatus here undefined or equal to 0. And in either case, the thing won't be greater than 0. So the only time you need to check the endpoints, like we did at the end of the last problem, is if you have a greater than or equal to, or less than or equal to. Like here, we don't have an or equal to, we just have a strictly greater than, which means it's all parameters. You can still check. Checking won't hurt anything. If you plug in +2, this factor downstairs is going to be equal to 0, which will make the whole thing undefined. If you plug in -2, this factor downstairs will be 0, which will make this whole thing undefined. So the inequality doesn't even make sense if you plug in -2 or +2. So they can't be a part of the solution set. And that means this is it. Any questions on this one? I know that this number line process might seem a little bit tedious. It might seem like, oh, it takes a long time. Is there a better way to do it? The answer to that is kind of. At its heart, this is the only way to solve these sort of inequalities. I will show you some tricks for speeding up this process. Basically, once we get to the section 4.1 or something, I'll show you a way to do this where you only ever need to test one point and you'll get everything else for free. But for now, we have to follow this. All right, I'll show you that shortcut. It has to do with multiplicities. If you've ever heard that term. After we talk about rational functions. Okay, so that's it. You've got plenty of inequalities to practice in your homework, and most of them look something like this. I'll just pull this up real quick. They are either linear inequalities or they're nonlinear inequalities that are in that form where everything's been pulled to one side and factored for you. So there's plenty of practice with exponents and fractions like we talked about on Tuesday. But then when you get down to the inequalities, there will be things like this, right? And here they're doing a sign chart instead of a number line. It's the same sort of thing. For the rest of these, you can do whatever you want. Those are linear inequalities. Then we have some more nonlinear inequalities. Everything's already pulled to one side and factored. So just make your number line, test a point from each region, and you'll be good to go. The last thing that I do need to show you today is some facts about domains and a few examples of finding domains. Before I get into the nitty-gritty there, I just want to talk about what a domain is and what we should have in mind when we're trying to find one. Okay. So, definition. The domain of an expression is the set of all numbers, or set of all the stuff that we are allowed to plug in for the variable. Or variables if there's more than one of them. But for us, a domain will always be a kind of one-dimensional thing. So the domain is just the stuff you're allowed to plug in. The way you find domains, stop. To find the domain of an expression, you look for these things I call domain red flags. So like, you ever been on a date with somebody and they start talking about how much they hate their ex, or how crazy their ex was, or how much they hate their mom, right? These are red flags, right? They're things that should make your brain go, I'm gonna be a little fucking careful with you. So functions, expressions also have red flags, specifically domain red flags. The red flags you want to be looking out for, there's two varieties. I'll be adding one more to this list later in the semester, but for now, two things you need to look out for. First, variables, any variable quantity downstairs in any fraction. The other thing you want to be looking out for is any variable stuff under an even root. Odd roots don't care, but even roots are a little picky. Maxwell, sorry, my dog. Maxie, down, down. All right. So why are variables downstairs in a fraction a red flag? Well, you know you're not allowed to divide by 0, right? I can take $0 and split it up evenly among my 10 friends. Every one of y'all motherfuckers gets nothing. But I can't take $10 and split it up evenly among 0 friends. That isn't something that makes sense. You can't divide by 0. So in this case, you need to make sure that the bottom of any fraction isn't going to be made 0 by something you plug in. And if you've got variable stuff under an even root, you need to make sure that the inside, aka the radicand, is not negative. And what it means to not be negative is to be greater than or equal to 0. Okay. So these are your two domain red flags, right? Just like someone complaining about their ex or talking about how, I don't know, fine, take your pick, they love Sean Hannity, whatever. Red flags exist, things that should get your attention and make you a little bit nervous or at least aware. When it comes to expressions, those red flags are variables in a denominator and variables under an even root. Let's take a look at an example. Let's find the domain of the expression x over x squared minus 5. And write the answer in interval notation. Okay. So do we see any red flags in this expression?
X in denominator.
Yeah, I've got these variables downstairs. So we need to make sure that this bottom is not going to be made 0 by anything in our domain. In other words, we need to figure out what numbers would make that bottom 0 and then kick those numbers out of our domain. That's the idea. So in order to ensure the bottom isn't going to be made 0 by anything in my domain, I'm going to find out what numbers would make the bottom 0. And then I'm going to pluck those numbers out of the real line. Everything that's left over will be the domain of this expression. So the bottom is going to be equal to 0 if and only if x squared minus 5 is equal to 0. And that's an equation that I'm sure everybody here could solve. I just add 5 to both sides. I get x squared equals 5. And then I can solve that by taking square roots. I get x is equal to plus and minus the square root of 5. And this tells me the domain is all real numbers except these guys. I think I'm going to put this dog in the phone real quick. Maxie, hey. Baby's car seat. You're gonna, yeah, you're gonna, okay? You're gonna All right. So that's the idea. The only way this expression is going to be upset is if I do something to make the bottom 0. The only thing I can do to make the bottom 0 is plug in the square root of 5 or the negative square root of 5 for x. So my domain is going to be all real numbers except for those guys. And if we want to report this in interval notation, it may be helpful to sketch it on the number line. I'll say this right here is the negative square root of 5. I'll say this right here is the positive square root of 5. And then I want everything except those guys. So I want everything over here, but not including this guy. I want everything in between, but not including either of these guys. And then I want everything over here. All right. So here is my set, my domain, sketched on the number line, but I need to give my answer in interval notation. So I need to figure out how to write this shaded set in interval notation. And you'll notice it's really made up of three pieces. There's this first piece, there's this middle piece, and then there's this last piece. So this is going to end up being a union of three different intervals. That leftmost interval is -infinity to -√5. And they both get parentheses. I don't want to include the square root of 5. That's the whole idea. I union that with this middle piece, which is -√5 to +√5. And then I union that with this far right piece, which is +√5 to infinity. And a fun trick, if you're looking at a set on the real line that is made up by just pulling out a few numbers, you'll always have the same number of unions as numbers that you pulled out. So oftentimes when I give a problem like this on a test, people will miss this middle guy. They'll say -infinity to -5 unioned with 5 square root of 5 to infinity. And they'll forget about this middle piece. The trick to helping you not forget that is to remember for every number that you pull off the real line, you're going to have a union symbol because that's a break, right? Where you need to join things together. So if you've got two breaks, that's three pieces. Questions on this example? Okay, I've got one last example for you here. I'm going to check time, see how we're doing. Got one last example I'd like to do, and then I'll let you guys go. Remember, you do have a homework set open in WebAssign right now. That homework set is due at the start of class on Tuesday, not like midnight, not like 11:59. It's due at the start of class. So I can be sure that you've all practiced and worked with this stuff before we move on. That's an important part of this class structure that's a little different from the way some profs do it. Remember, pretty much every day you will have a homework set due at the start of class, every Tuesday and Thursday. This Thursday, today, is the only exception, or test days. All right, here we go. Last example for the day. Let's find the domain of the expression. How about the square root of x plus 2 divided by x squared minus 5x? And again, answer in interval notation. Looking at this, what do you see?
X in the denominator?
Yep.
Or X.
Very good. Yeah, we got variables downstairs. So red flags. I've got variables downstairs. And what else?
A variable under the square root in the numerator?
Good. Yeah. Thank you, Suzanne. We've got variables under an even root. All right. So remember, to deal with each of these, we need to make sure the bottom isn't 0. That means we're going to have to solve an equation. For the other guy, I need to make sure the inside is greater than or equal to 0. And then in the end, we're going to have to take the overlap of these two sets. We're going to have to intersect these two sets rather than unioning them. We need to make sure that we're not getting in trouble with either of these things, which means we need to throw away anything that causes either of those sorts of trouble. A quick word, if this was x squared plus 2 under the radical, then the inequality you'd have to solve there is nonlinear. So it's entirely possible that within one of these problems, you have a nonlinear inequality to work with. Just a thought. All right, dealing with item 1, if I set the bottom equal to 0, then I'm saying x squared minus 5x is equal to 0. How do you solve this equation?
You FOIL it?
Kind of, what like backwards foiling, right? So foiling is like to distribute, to expand things. Here, I want to kind of undo that process. I want to factor. And what we see, this is not a bad one. Both terms have an x factor that I can pull out. When I factor out an x, what's left is x minus 5. Everybody sees that? If I were to redistribute this x, x times x is x squared, x times negative 5 is negative 5x. So we factor, and then set each factor equal to 0. So the numbers which will make the bottom 0 are 0 itself and 5. So from these, we learn that x cannot be equal to 0 or 5. And then following the other red flag, we know that we need the inside of this square root to be greater than or equal to 0. The inside of that square root is x plus 2. So that means I need x plus 2 to be greater than or equal to 0. And this is a linear inequality that we end up with here. X plus 2 greater than or equal to 0 is linear. So I can solve it just by isolating x. That means x is greater than or equal to negative 2. So sort of these are the things I have. I need x to be greater than or equal to negative 2 and not equal to 0 or 5. If I plot those on a number line, I'll say negative 2 is over here, and maybe 0 is here, and 5 is here. X is not allowed to be 0, and it's not allowed to be 5. So I need to kick these guys out. And in addition to that, x needs to be greater than or equal to negative 2. So I can't have anything from over here. So it all has to come from the right of negative 2, but then I have to hop over 0, and I have to hop over 5. So this shaded set down here is my domain. I want to take a second. Does anybody have any questions about either of the two purple steps here that are numbered? Like how we did any of those things or why we did any of those things? It's okay.
I'm kind of confused as to where we were square rooting x plus 2 and then turned it into an inequality and it disappeared. Is that just how it works?
Well, so sort of, yeah. So remember that the rule is if you have variables under a square root, you need the inside to be greater than or equal to 0. What's going on here is that you can't take the square root of a negative number, right? If I try to take the square root of a negative number, I get like weird complex number stuff out.
Yeah.
So when we're finding the domain, I need to make sure that this square root up here doesn't ever have negative stuff inside of it. The way to avoid that is to make the inside greater than
zero.
or equal to
Okay,
So that's
that
all.
does make sense. All right.
Cool, yeah. So we're not doing any crazy algebra steps. It's just like, how do I keep this thing happy, basically?
Yeah.
Seriously, expressions like this, they've got personalities. They really do. It's a fun way to think about things. They can be emotional critters. They really can be.
True.
Any other questions about the first two purple steps here? Why we're doing it, or where it came from, or what we did? Okay, then the big step after that is figuring out like how to sketch this from these things. So are there any questions about how we go from here to here? Feeling pretty good? So the first guy says X isn't allowed to be 0 or 5, so I just pluck those out right away. And then the second one says, in addition to that, X has to be greater than or equal to -2. So I say, okay, everything to the right of -2 is good, except 0 and 5. And since this is a greater than or equal to, I'm using a bracket, or if you wanted to use the other notation here, it would be a filled in thing here, open thing here, open thing here, like that. Either notation is fine. I think WebAssign uses the parens and bracket notation. I'll use either one. So in the alternate notation we used at the start of class, you could sketch this domain like this. Same thing. All right, so now I just need to write this thing in interval notation. Help me out. What are my endpoints?
Closed bracket, -2 to 0, and then a parentheses, and then union 0 to 5, and then union 5 to 0, all parentheses on the rest.
Let's see.
Or if I meant union 5 to infinity. I read that wrong on my
Oh,
paper.
very good. Very good. You got it. All right, that's it. So this is it. This is my domain. And it's a somewhat complicated set, right? Like it's got closed things and open things. It's got finite length things and infinite length things. But we can do it. It's not too hard to arrive at. We just have to remember to watch out for those red flags and then how to avoid the trouble associated with those red flags. That's it. That's everything you need to get through this first homework set, which is due for you guys on Tuesday at the start of class. Please work on it. If you've had any trouble getting into WebAssign, like getting registered, getting your access code to work, please copy and paste this message from chat that I sent out at 12:39 with the Zoom link for the registration help. That came from Marlena Hadfield or Hanfield, our Cengage rep. So they'll be coaching you guys, getting you through the registration process in case there are any problems, because Cengage did change their website a little bit this term. If there's anything else that you need to talk, you got questions, curiosities, concerns, anything like that, send me a Canvas message, drop by my office hours, or send me an email. Remember, if you are new to the class, you absolutely need to read the syllabus, which is linked in Canvas on the home page here. So please save a copy of it to the computer, read it. A good time to read it would be as you watch the lecture from Tuesday, because I go through the syllabus in that lecture, and the recorded lecture from Tuesday is right here. Just follow this link. That's it. If you got anything else you want to ask me, I'll be around answering emails, stuff like that. Otherwise, I will see you guys on Tuesday. Take care.
Thank you.
Yeah.